Let me start by thanking the organizers to give me a chance of speaking here. And I'm a radio astronomer and a teacher in the University of Pretoria, and I'm going to talk today about how machine learning and AI techniques can be applied to what I do, that is radio astronomy, extragalactic radio astronomy in particular. Let me just take a minute to say that 2 weeks ago, I presented a version of this talk in another meeting, which was also quite broad. And what we found in the discussion was that no matter what we work on, whether it is radio galaxies, protoplanetary disks, gravitational lensing, AGNs, there are common problems which all of us are working on simultaneously, and without knowing that we are working on very similar problems. So what I want you to remember while I discuss radio galaxies is that some of these things might be applicable to what you are doing. And after all, that is the point of this meeting, to bring us together and form collaborations where possible. The other common point between the two meetings was that I always got the pre-lunch slot, and organizers say that there's nothing personal. Let me proceed. So forgive my obligatory slide on big data in astronomy. By now, I think everyone here knows that we are indeed in the era of big data, with terabytes and petabytes of data sizes streaming through. Of course, these data sizes refer to raw data, and there is also another dimension, that is the output product. So the aim here is to go from something like this, that's your raw data, to something like this, which you can interact with, in a sense. And we know that, well, as a good radio astronomer once said, a radio image is like a sausage. You don't want to know what went into making it. So there are a lot of things which go into going from this to this. And those could be flagging, cross-calibration, self-calibration, DD self-calibration. You can replace your own pipeline with this, and you have a very complicated process which has many bottlenecks, which may be sped up or not. And that is where facilities like ILIFU, the proto-SRCs which were discussed, come in, and we know they can help us in many ways. So just a quick acknowledgement here. This image was indeed made with ILIFU, and many of the results I'm going to talk about today were enabled by ILIFU and IDEA. Let me take a chance to thank them. So fine, so we can do something about this process and speed it up, but that's not what I'm going to focus on today. That's a whole different topic. What do you do once you have your images? Let me take the very basic box standard approach of end-to-end image analysis. What's the big deal about the era of the big data? You might say that image is already a reduced component of the whole thing. You're away from the big data. The issue here is that when you're working with precursors and pathfinders of SKA, for example, the images you get are fundamentally different from what you're used to. Take an image. If you want to extract science from it, what you do is take segment sources and define them, and then you can do all sorts of things like cross-match with optical, infrared, X-ray data. You can find novel objects, arcs maybe, whatever. You can go on, add your own types, which might be looking for transients, looking for supernovae, whatever you want. The trouble is that these images, for example, here is a deep 2 field. It's one of the deepest fields in radio continuum known to us. And you can look at all the dots here. Even switching off the light is not helping, but if you look at the original image, you will see that the density of sources is extremely high. Not only that, it's not all point sources. It's extended sources mixed with point sources, for example. So I have just highlighted some of the sources which I might be interested in. And the challenge here is to separate the two. And I can assure you this is a non-trivial job. Sources like this, what I'm talking about, radio galaxies, take the example of Cygnus A, which is the most famous radio galaxy. You have the nice, well-defined lobe and core and hotspot structure. And galaxies like this can be classified with, say, Vanneroff and Rayleigh scheme, class 1, class 2, brightness in the center, brightness at ends, and so on and so forth. It was devised by these two people. And Bernie, as we know, is deeply related with the SKA project. Now, even if you took this very elementary approach to start with and decided to classify your images, there's a long history of machine learning techniques being applied to radio images, going back to almost 2002. Funnily enough, in the initial approaches, it was said that machine learning techniques are not working. Let me go to some, or CNNs are not working, let me go to something like decision trees. And this is one of my favorite papers. It has the same concerns as any modern AI, machine learning, astronomy paper. Then you see a sort of jump in 2015-16, you see self-organizing maps, which has been recently updated. And they found very novel objects and stuff like that. Then in 2017, for the first time, me and that's Arun, we applied a version of AlexNet to this problem, I think for the first time ever. And we got good results. We put our model online. That's called Toothless. It's not a commentary on its effectiveness. In fact, it's quite good. And so on and so forth. So we see that each iteration, each paper here, which I have mentioned, it has been a refinement and on previous efforts, trying to do better and better. What's common in all these studies is what I didn't mention. All of these are based on older archival data. So the sources used here are from FIRST. That's a very beloved older radio survey. Unfortunately, as I mentioned earlier, the images from FIRST and from MeerKAT, for example, they are very fundamentally different. And it is as it is supposed to be. For example, take this source. What is this? Where does it fit in the scheme I told you about? Is it an FR1, FR2? I'm cheating here a bit. And this is a very complicated source discovered by MeerKAT. And you can see that even here, it's pretty difficult to make out what it is. And I can tell you that the older versions of this source observed by other telescopes were not as illuminating as this image is actually. So even in the sources which you have previously observed, you're going to discover something new. This is not just about discovering new categories of sources like AUX. So here I want to point out that getting physics from these sources is, of course, as someone said, there is nothing quite as useless as a radio source. So we do need optical cross matches. I just wanted to mention a very vital piece of work done by Precious and Sarah at looking at these sources and finding redshifts for them. So this understanding that the current schemes are not enough has been growing in the community for the past few years. One of the papers in this is radio galaxy classification tags, not boxes. So you don't put them in hard categories. You put them in assign tags to them. And that way, your data is actually useful to the wider community, because not everyone is interested in FR1s and FR2s. People are interested in, is it a steep spectrum source? Is it an AGN? Is it a star formation plus AGN? And so on and so forth. But going back to the pipeline, which I mentioned, end-to-end, pieces of it are already in place. So this shows you this first bit, the most trivial, going from the radio image to segmentation. And this was done by using UNet, which actually was defined for medical-based imaging. And it turns out, if you apply it, it's an order of magnitude faster than the traditional tools which are in use. This was done by Cyril Kupa, our student, who recently received an award for this effort, and Dr. Marcelin Atemking. We can also look at, is it wise to discard the archival data completely, or can we still use it? And Hidyan, who was a former student and currently is working at SAAO, was involved in this effort. I understand now that he's carrying on his fascination with radio galaxies using MeerKAT data at SAAO also. But at some point, we do desperately need new labeled data, and that's the core of supervised, not just supervised techniques, because even for unsupervised techniques, you do need to tally your results somehow. And that's where one of our students who has taken the lead in this, Chaivo, he's a Sarajevo-funded student, and who has made the largest catalog of bent-tailed objects ever using the MGCLS survey, that is a MeerKAT survey which has been recently made public. And you have heard about this bit. Are there new anomalous objects which we should be hunting for? Maybe orcs, maybe X-shaped radio galaxies, maybe dying radio galaxies. Our student, Jamie, is actually looking at this possibility using something called the Siamese network. Ultimately, as I mentioned, we need to explore this pipeline in full. While the pieces are there, it needs to be a coherent whole. And then can we use it in tandem with data reduction pipelines like Process MeerKAT, Caracal, RTIP, OxCat, the IDEA pipeline, and so on and so forth. So what we are going to try going ahead is anomaly detection in SK precursor and pathfinder data, multi-resolution, multi-wavelength investigations with MeerKAT and LSST, synthetic data generations. Can we replicate these rare objects with synthetic data? Can simulations of complex radio sources help us in this? And that is what we are focused on, and we are lucky to have people at University of Pretoria who are interested and committed to these efforts, including Dr. Anna Bosman, Fernando Ventura, our IDEA PhD student, and Gaurav Giri, our incoming Sarajevo postdoc. So while I have given you a quick summary of what we are doing, how does this translate to this meeting? And how can BRICS Astronomy Working Group help? Just listening to the talks over the past 2 days, it's very clear that we are, to some end, working on some very similar issues. The expertise is there. If I just confine myself to radio astronomy alone, it's clear that many of the BRICS partner countries already have a tradition, as well as cutting-edge experience in these matters. The AI community, as will become clear, I hope, over the next 2 days with the hackathon, is widespread and is interested in helping us with these matters. So we have the people needed for tackling these issues. All we need is effective collaborations amongst us. And BRICS actually is a very good platform for such things. As a quick example, I'm just going to show you a nascent effort ongoing. So for example, we are looking at detecting neutral hydrogen in image cubes, not just a single continuum image, but a cube of images. And that's a problem which hasn't been tackled fully. And we are collaborating with Dr. Arun Onion, Dr. Sajid Philip, and Lynn Abraham, who has taken the lead in this effort. He's a PhD student, and all of them are based at the Artificial Intelligence Research and Intelligent Systems. This is based in Kerala, in India. And efforts like this, where we join forces, can obviously be helped by BRICS. With that, I think I'm within my time. I'll just show my conclusions. So the takeaway messages are this: we need new approaches in AI applications for effective science exploitation of these wonderful new images and data, let me say. Because even though I have just showed you image domain stuff, it's not to say that this is not applicable to issues like RFI hunting in raw data. Engagement with new and sensitive data is the key to success because, as I said, it's very different from what you're used to from previous telescopes. And effective collaborations between BRICS partner countries can help consolidate. To me, that is the key thing, and speed up these efforts. With that, let me stop. And if you have any questions, I'm happy to take them.